In this segment, we're going over the Drake equation. The Drake equation is a formula for the number of communicative civilizations in our Milky Way galaxy. First thing you should notice is that it's a formula. Formula is just another word for equation. So here is your equation. Next thing you need to notice is that we're talking about something that we want to obtain, and we want to obtain a number. So you'll see an N where we mean number. And since it's got a small c, that small c means communicative civilizations. So we are looking for the number of communicative civilizations in our galaxy. The number of communicative civilizations in our galaxy. Let's look at the individual parameters on the right side of the equal sign. Let's first look at N star. So N star is the number of stars per galaxy. So you want to think of a number. How many stars are in the Milky Way galaxy? So don't guess, go look at the textbook and come up with a number. An optimistic person might assume the number of 2 times 10 to the 11th as the number of stars in the Milky Way galaxy. Now let's look at this F sub small p. Now F sub p, the p stands for planets. So F sub p, F stands for fraction, and F sub p is the fraction of stars with planets. So let's say you assume that there are 2 times 10 to the 11th, or 200 billion stars systems in the galaxy. Of these 200 billion star system, what fraction of them would have planets? An optimistic person would say the fraction is 1 over 1, or 100%. A pessimistic person would say something like 1/10. So you need to think of a fraction. We're going to be optimistic. We're going to say 100% of all the stars have planets around it. So the fraction would be 1. Now let's look at N sub Hz. So N sub Hz is the fraction of planets per star that lie in the habitable zone. So N sub Hz is the number of planets per star that lie in the habitable zone for long. So N sub Hz is the number of planets per star that lie in the habitable zone for longer than 4 billion years. So instead of thinking of the number of planets per star that lie in the habitable zone, let's think about this. We want to find out what is the fraction of the planets that have water on it. So you have these planets, they're going around their stars, and all these stars are in the Milky Way galaxy. What fraction of those planets have water on it? And those planets have to be longer than 4 billion years old, or the star has to be longer than 4 billion years old. What's that fraction? The optimistic person would say 100%. That if a star is older than 4 billion years, then any planets that are around it will have water on it, if they are in this zone where water can be in the liquid state called the habitable zone. So we're going to allow this fraction to also be 1, being the optimistic person that we are. Let's go look at F sub L, capital L. So F sub capital L is the fraction of suitable planets on which life begins. So let's say you've got the Milky Way galaxy and you've got stars in it, and you're looking at the stars that have got planets in it, and you're looking at the planets that are in the habitable zone. In other words, they've got liquid water on it. So of those planets that have liquid water, what's the fraction that would have life, meaning bacteria or amoeba life in the water? The optimistic person would say, if there's water on the planet, there's got to be bacteria or amoebas. So we'll say 100%, or 1 out of 1 fraction, which is equal to 1, so the fraction would be 1. The pessimistic person might say 1/10 or 1/100th. So we're going to be the optimistic person and say 1. Now let's look at this F sub small l. So F sub small l is the fraction of planets with life where life evolves into intelligent life. So now you have planets that have water on it, and of those planets with water that have bacteria in it and amoebas, what is the fraction of those planets with bacteria and amoeba that they will evolve into some kind of intelligent life, such as humans? The optimistic person would once again choose a 1 out of 1 as a fraction, or 100%. If there is amoeba or bacterial life, then eventually that amoeba or bacteria will eventually evolve into intelligent life. The optimistic person would choose this fraction of 1. The pessimistic person would choose a fraction like 1 out of 100 or maybe 1 out of 1,000. We're the optimistic person, so we're going to choose 1. Now let's look at the last fraction, the f sub small s. So f sub s is the fraction of a star's existence during which a technological society survives. In other words, your life or your human life form or your technologically advanced life form has evolved to the point that it can communicate, it has developed weapons of mass destruction. So what's the probability that they don't kill each other off and so there's no one left to communicate with? The optimistic person would suggest a fraction of like 1 over 10,000. That's the optimistic. In other words, there's a high probability that the society will not survive. You'll also have to take into the amount of time that the star exists, because young stars die sooner and older stars live longer. So the age of the star comes into a factor as well. The pessimistic person would choose something like 100 million, 1 over 100 million, or a very, very small chance that that whole star system would continue to exist, or that planetary system. We're the optimistic person, so we will choose the 1 over 10,000 fraction. So let's put each of these values into the Drake equation and solve. So here's our Drake equation. We'll carry the equal sign down, and remember, we're looking for the number of communicative civilizations. And the first number we need is the number of star systems in the Milky Way galaxy. We had selected 2 times 10 to the 11th. So the next one we need is our f sub p, the fraction of stars with planets, which we assign the fraction to be 1. The next one we have to look at is n sub hz. N sub hz is the number of planets per star that lie in the habitable zone or have water, and the star system is longer than 4 billion years, and we chose a fraction of 1. The next one we're going to look at is f sub small l, and f sub large L, and the f sub large L is the fraction of suitable planets on which life, such as bacterial life, begins, and once again we had chosen a fraction of 1. The next term we'll look at is the f sub small l. F sub small l is the fraction of planets with where life evolved into intelligent life, and once again we chose the fraction of 1. And then the last one we have to look at is f sub s. And f sub s is the fraction of a star's existence during which a technological society survives, and we chose 1 out of 10,000. So let's solve. We have 2 times 10 to the 11th on the top, multiplied by 1, multiplied by 1, multiplied by 1, multiplied by 1, and then divided by 10,000. So that's the same thing as 2 times 10 to the 11th divided by 2, and since there's 4 zeros, times 10 to the 4th. And so now we can see that 2 divides into 2 easily, and that will give you a 1. We keep our multiply, we keep our 10, and we're going to take our 11 and we're going to subtract 4. And so that will give us a 1 times 10 to the 7th. And that's the same thing as 10 with 6 zeros, or 10 million. So the optimistic person would find 10 million communicative civilizations inside the Milky Way galaxy with which we as humans can communicate with now. So remember that the Drake equation is a number of civilizations in our Milky Way galaxy that are at a technological level that they're able to communicate with us humans, and we can communicate back with them. So we estimate as pessimistic 10 million civilizations. A pessimistic person would come up with an even smaller number of civilizations.